So first off, heat of combustion. So when you increase carbons, what happens to our heat of combustion?
Increase.
Yeah, we increased our heat of combustion. As what happens to the boiling point?
Decrease.
Increase or decrease?
You're increasing your heat of combustion. You're not increasing.
And then you're going to increase our boiling point, right? If we increase the number of carbons.
Yeah.
Because of why? Why does this happen?
Surface area? Right?
Yeah. Interlocking forces. We think, well, heat of combustion, there's just more bonds to be broken and then reformed to, because heat of combustion we're forming carbon dioxide and water. So when we form carbon dioxide and water, we're forming a lot more bonds. So we have more carbons, more bonds get formed, so more heat's given off. Boiling point increases because of the surface area. If we remember dispersion forces are just the fact that you have electrons moving through our carbon chain, and some might randomly be on one side, more on the other. So there'll be a slight interaction there. If you have more electrons, there's going to be greater intermolecular forces. Okay. So, but what happens if we have the same number of carbons?
Then
it's all about
the branching.
Branching. So what happens is we increase branching.
Decrease your heat of combustion, but increases stability.
Yeah, and it would decrease our boiling point. Yeah. So that's just like the fact that both of these molecules, our pentane and our neopentane, both have 5 carbons, but this one has a lot more surface area to line up against, where this one there's less interaction there because it's bulky, it's protruding out.
So increasing your branching, so the compression go down and then more stable.
And increase stability, yeah.
Okay. So more branching you have, more stable you are.
And this is, excuse me, I don't know why I have a cough. And this is why, how the book explains it. If we think of our energy level here, our delta G, if something is exothermic, it's lower, right? So how would I say this? So you think of this like, here's where, let's say we have 5 carbons here. Let's go this way. There's that molecule here. But here's where our neopentane is. When it heat of combustion, right, it breaks up and it forms carbon dioxide and water. So it forms the same product. And it gives off energy, so we know it's exothermic. Well, if it gives off more energy, that means this pentane is higher up in an energy level. The neopentane gives off less energy, so it's lower on the energy level, because the delta G is going to be smaller than this delta G. So the fact that this is lower on the energy level, it's more stable because things that have lower energy have greater stability. So that's how the book explains why we say that something with more branching is more stable, just because it's going to have less of a delta G.
But like I thought for these ones, they have the same number of carbons, but I don't think they have the same number of hydrogens. So maybe I miscounted.
Which ones?
Just like it was the last.
I don't think the hydrogens matter.
So it's just like the number of carbons that matter?
The hydrogens will play a role, because the only way you're going to have less hydrogens.
So like the circle, right? Like we have anything more. Maybe I just counted wrong.
Well, this one, let me draw these here. Yeah, these, because this one's in a cyclo group. No, these will have the same number.
Of hydrogen?
Yeah.
Yeah. Okay.
So they do, because if you think, so they have the same number of carbons, right? 1, 2, 3, 4, 5, 6, 7. 6, 7. 1, 2, 3, 4, 5, 6, 7.
Yeah.
So this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14.
Mm-hmm.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. So this one's stability, yeah, heat of combustion is used, and it makes a lot of sense that cyclopropane is going to have the highest energy because the least stable, because it's a propane group. Those bonds are like really forced, tight
Like the
together.
strain.
Yeah, and then pentane a little bit, but cyclohexanes are most stable cyclo group. So we should expect this to have the lowest heat of combustion out of these three.
Why is that again?
Because these angles are, with their hydrogens off of it, are closer to the 109.5 that we would expect an sp3 to have.
We should ask him about that question, Brian, with the angle. Like there's a question it was a cyclohexane. It asked about a carbon bond, so there's 3 carbons, and it asked about the angle. Like the size of the angle. And we thought it was like 60, but it was 120.
This one.
That one? I didn't really understand why. It said a planar, so what does that mean?
A planar,
It's like a flat?
yeah, you force it to be flat. That's why it goes to the chair conformation. Let me move this here. Is so by going to the chair, this angle here is closer to the tetrahedral shape. But when it's like flat, like a planar, and it's hard to see with the model kit, but it forces it to be a lot wider here.
Mm-hmm.
But by twisting it, it's closer to the 109.5 it should be at.
So why would it be 120?
What are your options on it?
109.5, 1690.
I think the way you would determine something like this is, well, if it's planar, this bond has got to be greater than 109.5 because it's forcing it out more. So you know it's going to be the only answer that's above 109.